All right, this is maybe for me the most fun part of Calculus 1, where we will take integrals and use them to calculate volumes of three-dimensional solids. Now, when I say solids, I'm talking about solids of revolution. Okay, so I'll show you what I mean. Let's say we want the volume of something that's going to rotate around this axis of rotation. So we're going to rotate this way. And let's say that we want to rotate this region here around, so this is a two-dimensional region. You could shade it in, right? Shade it in. We want to rotate this region around this line of symmetry. Let's kind of draw what that would look like, okay? So now I'm going to use a lighter color here. So this is kind of the region we have. We're going to rotate around this axis of rotation. And what it would look like is I need to draw a mirror image of this the best I can down below. So I'll start by trying to mirror this point, and then I'll try to mimic the curve, something like that. So we've got our mirror image above and below, and then when I rotate it, what happens is I get this circular cross section, okay? So if you can use your imagination, this looks kind of like a bullet in 3 dimensions. And so if I wanted the volume of this and I wanted to use integrals, what I'd have to do is cut it into an infinite number of pieces that have the same behavior. And so when we do what are called volume by disk, we're going to slice this, and this is important. When we use disk, let me use a different color here. We slice perpendicular to the axis of rotation. Okay? So here's what I mean. Since our axis of rotation runs this way, we're going to slice this way. Let me show you what that looks like. When I cut this thing into disks, it's very much like taking a two-dimensional region and cutting it into rectangles, okay? It's a little bit harder to draw though. But if I used right endpoints, then my first disk, if I work from the right to the left, the right endpoint would be here. And all I do is I draw a horizontal line over to give this disk a thickness, something like that, okay? And I don't want to draw a bunch of these, so I'm going to make it pretty wide. And then I'm just going to mirror this curvature here, like this, something like this. Okay? And so what we have is our first disk that's going to be used to approximate a volume. And so in 3 dimensions, maybe it's like a coin or something, right? This is the edge of the coin, and then this is the side of the coin. And so we've got a disk here. And we'll talk about how to find the volume of a disk. So let me erase the original image over here and talk about the volume of a disk. So disk volume, really it's just a cylinder, okay? It's just a cylinder, but you take the area of the circle, which is pi times the radius squared, and then you multiply it by the thickness of the disk. So I'll call that thickness T, okay? So I'll call that thickness T. And so what we do here is we calculate the volume of this disk. But if I want to approximate the volume of the whole bullet, let's call it, I'd need to have disk running all the way across. So my next disk would start here, and I would run the same thickness like this, and I'd mirror that curvature, and then this would be the edge of my second disk. And I don't want to draw the rest of it because it's kind of hidden behind this. You're basically going to stack coins next to each other. And maybe I'll fit 2 more in there. It's not going to be perfect, but just enough to give you the idea. And then the next one's going to be here and look something like that, okay? So this is like 4 disks stacked side by side. Now, clearly, if I add the volumes of these particular 4 disks, I'm going to get too much because you can see that they are bigger than the solid dictated by the curve. So this would be an overestimate of the volume in this case. But just like with rectangles in 2 dimensions, all we have to do is shrink the thickness of these to be nearly nothing and have an infinite number and add all of them together. Okay, so that's the idea here. Now, that means that the thickness will be our dx or dy because that's going to be infinitely thin. So this guy here, this thickness will be dx or dy. And you can see in this case the thickness of this disk is measured horizontally. So in this case the thickness would be dx. Okay? So let's look at in practice how we would do this. We don't draw those disks every time. We draw a representative of one disk that's infinitely thin, which makes this process much easier. So if I were to draw the same thing, here's our region again. We're rotating about this axis. Draw the mirror image then. There's our 3-dimensional solid. Then what we would do from there is we would pick an arbitrary disk between the beginning and the end of the solid, maybe right here, and this is my perpendicular slice to my axis of rotation, my perpendicular slice. I would locate the point above and the point below, and then I would just draw a ring. When you make an infinitely thin disk, you just get a ring that has no thickness. So we're just imagining that this guy's infinitely thin now, and of course, this would be the radius, right? That would be the radius. So you have pi r squared times the thickness. The thickness here is measured as dx, okay? So if you wanted the volume of this entire solid, you would do the infinite sum, so that's an integral, from, let's say, A to B, and those are x values because this is dx, and it'd be the volume of one disk is pi r squared times your thickness dx. Let's move this over. And so the key here would be, since this is dx, your r would have to be in terms of x, okay? So it's no big deal. This is the volume of one disk, and then you just add all of those together using an integral. Okay, now let's talk about the orientation here of the different types of disk. If you have vertical disk like we just saw, vertical disk like this, then the volume here is going to be pi times the radius squared times your thickness, which is measured horizontally, so that'd be dx. If you have a horizontal disk, and the reason you would have that is if you had a vertical axis of rotation, right? If you were rotating this way, you'd have a horizontal disk. The thickness would be dy measured vertically, so the volume in this case would be pi times your radius squared dy. So in this case, you'd have to write r as a function of y, whereas in this case, you'd have to write r as a function of x, okay? And so that's the concept of volume by disk. I'll make another video with several examples.